Okay, Unit 1 guided notes. So Unit 1 is all about limits. Let's look at the essential learning outcomes first. So these are the main things that we need to understand in Unit 1. Being able to read, write, and evaluate limits using their properties. Using the limit definition of continuity to verify points of continuity and discontinuity. And we have two theorems in Unit 1. So verifying conditions and justifying the conclusions of the limit existence theorem and the intermediate value theorem. So we're going to learn about limits. We're going to talk about continuity versus discontinuity and the limit existence theorem and the intermediate value theorem. So there's a lot you're going to learn in Unit 1. Those are the three things that you'll be assessed on. So where have we been and where are we going? Algebra, everyone's favorite, is the study of generalizations of arithmetic operations. Operations are just add, subtract, multiply, divide. Geometry is the study of shape. And calculus is the study of continuous change. So calculus means small pebble in Latin. It was developed in the 19th century by Newton and Leibniz. And its uses in the 20th century are widespread throughout science, engineering, and economics. So we're starting with limits. There's three big ideas in calculus: limits, derivatives, and antiderivatives. So without limits, there would be no continuity. Without continuity, there would be no derivatives. Without derivatives, there would be no integrals. Integrals are the same as antiderivatives. And without integrals, there would be no calculus. So we're going to start with slope, which we should all be familiar with, to define limits. So our first definition, slope. Slope is a loaded word. It means a lot of different things. In general, it means a rate of change. Anytime we're finding a rate of change, we're finding the slope. Slope formula is a difference quotient. Difference quotient meaning a subtraction fraction, right? Difference means subtraction, quotient means fraction, and there are many forms of it. So I'm sure you know slope as rise over run. That's graphically. This is delta y over delta x, where the triangle means change in. So we have a change in y over a change in x. Y2 minus y1 over x2 minus x1, that's the point formula. Given 2 points, we find the difference in the y's over the difference in the x's. And f of x2 minus f of x1 over x2 minus x1, this is just function notation. So there are many ways to represent slope. Remember, f of x is a y value. Is the y value at x. The units for slope are always the y variable, the output, per the units of the x variable, the input. Right? The y variable is on top over the x variable, which is on the bottom. F of a is a y value of the function f of x at x equals a. The point would be a comma f of a. To derive a formula means to create or deduce, prove a formula exists from already known facts and formulas. So we're going to derive the point slope equation of a line using one of the known slope formulas from above. So let's start with the most known slope formula, the point formula, y2 minus y1 over x2 minus x1. So this is our given. We know this is true. If I multiply by x2 minus x1, it's going to clear my fraction. Right? I multiplied the denominator to the other side of the equation. And if I rewrite it, so I have the y's on the left, m times the x's on the right, right? That's just reflexive. Something equal to itself can be in any order. Now, in the point slope formula, we only need one point. So I'm going to eliminate the y2's and just leave the y1 and x1. So we use the point slope formula often. It's the most commonly used formula when we're trying to write an equation of a line. M is the slope, x1 comma y1 is the point. So now let's start with that formula. To derive the slope-intercept form of an equation. Well, I can distribute the m, I can distribute the slope, and I can add y1 to the other side. And this portion, m times x1 plus y1, that's just a constant. And it happens to be the y-intercept, which is commonly named b. Now, can we prove that b is not just any constant but the y-intercept? Well, the definition of the y-intercept is the y value when x equals 0. So if we start with that known formula, slope-intercept, y equals mx plus b, and we let x equal 0, then we get y equals b, where b is the y-intercept. So we just derived some basic formulas. These formulas are the foundation of algebra, and algebra is the foundation of calculus. So we just talked about rate of change being slope. Average rate of change, or denoted AROC, is the slope between 2 points. So average rate of change is the slope between 2 points, or the slope of a secant line. A secant line goes through 2 points. So the average rate of change of f of x on the closed interval from a to b is f of b minus f of a over b minus a. Now this formula should look familiar because it's the function notation of the slope formula. So now we're going to write the average rate of change of y, which is equal to f of x, from x equals a to x equals a plus h. So in calculus, h represents a small change. It has to do why the word calculus means small pebble. So h is a small change. So we're going to go from a to a plus h. So this is a point that's really close to a. So our point is x equals a, y equals a plus h. So the average rate of change is going to be f of a plus h, the y value, minus f of a, the other y value, over a plus h minus a. Now we can simplify that. Because in the denominators, the a's cancel, and we just have h, that change, that small change from a to a plus h. So this is the average rate of change of f of x from a to a plus h. So note, this is a notation formula, which means it looks nice as a definition, but it's not all that useful in practice. When we see it, we want to think of the synonyms it represents, of which there are many. We want to think of slope, rate of change, or derivative. And the word derivative, which we're getting ready to define, you'll see is also a synonym for slope. So the derivative is a rate of change, which we know as slope, but it's the rate of change or the slope at a single point on a curve, not between 2 points, at a single point. So it's the slope of a tangent line. Tangent line goes through 1 point, and that point is called the point of tangency. So it's no longer an average rate of change, it's an instantaneous rate of change, right? It's the rate of change at 1 point, so at 1 instant. So we simplify that by IROC for instantaneous rate of change. So some notation. This is read as f prime of a is the derivative of f of x at x equals a, or the slope at x equals a. So looking at tangent lines for these points. So a is at a maximum. The slope at a maximum or a minimum is always 0. So the slope at A and the slope at D are both horizontal lines. And we know that the slope of a horizontal line is 0. At B, the slope is going to be negative because the function is decreasing at that point. At C, it's going to be positive. So m is less than 0, meaning it's a negative slope. M is greater than 0, meaning it's a positive slope. And again, at point E, we have a positive slope. Function is increasing at point E. So it depends on the point you're at on the function to determine its slope. The slope, or the rate of change, is not constant throughout. It changes throughout the function, right? Starts out positive. We start out increasing. And then it's 0 at the maximum. Slope is negative. It'll be 0 again at this minimum. Slope is positive, 0 at the maximum, negative, 0 at the minimum, and then it ends positive. So we just went from average to instant rate of change. And now we're going to connect the two. Okay, we're going to derive the equation of a tangent line of f of x at x equals a. So we need two things for an equation of a tangent line. We're going to be writing equations of tangent lines all year. So we need two things. We need the point and we need the slope. Well, the point is x equals a. Therefore, y is going to equal f of a. The slope, usually denoted as m, the calculus notation is f prime at a. So if we start with our known slope formula, m equals y minus y over x minus x. We're going to replace m with f prime of a, calculus notation. We're going to replace the second y with f of a, the y value from our point. And we're going to replace the second x with a, the x value from our point. So now again, I'm going to multiply by the denominator to clear the fraction. And now I can rewrite it with my y's on the left and my x's on the right. So y minus f of a equals f prime of a times x minus a. And this should look very similar to our point slope formula, because again, what we need is one point and the slope. Now it's just in calculus notation. The point is a comma f of a, and the slope is denoted as f prime of a. So it's still y minus y equals m times x minus x, replaced with the calculus notation. Okay, the instantaneous rate of change, the slope at one point, can be estimated by using an average rate of change. So the instantaneous rate of change can be estimated well if the points used in the slope of a secant line are extremely close to the point of tangency. So as long as the points are really close together, they will give you a good estimate for the instantaneous rate of change. So if x equals c is between x equals a and x equals b, then f prime of c, the slope at c, is approximately f of b minus f of a over b minus a, the slope between the 2 points. Now, again, the closer a and b are to each other, with c in the middle, the better the estimate is going to be. So if we look here, C is a point between A and B. So if we look at A and B, and we look at the blue line first, the slope of the secant is the average rate of change between A and B. And at point C, we will have a slope that is approximately equal to the slope between A and B. Now, if we move those points A and B in closer to C, the better our estimate will get. So if I move A here and B here, well, now the slope of that line is going to be closer to the slope at C. So the closer A and B are to each other, the better the estimate of the instantaneous rate of change for the point in between them. If we look at this graph, x sub 0, that's a starting point. X sub 1 is our ending point, so our A and B. Remember, delta x means change in x. So the slope of the secant between A and B is drawn for us in blue. So there must be a point C in between that has a very similar slope, or the slope would be parallel. Again, if we move A and B in closer to C, the better our estimate is going to be. Okay, the most common application in calculus is motion. And if you've taken physics, then you should be familiar with position, velocity, and acceleration. If you haven't, you're going to get familiar with it here in calculus. So position is where the object is at. This is the original function. So it's denoted as P of t. You'll sometimes see X of t or S of t for position, where t equals time. So it's a function of time. Speed is how fast an object is moving. Speed equals the absolute value of velocity. Velocity is how fast and what direction something is moving. And velocity is the first derivative of position. So if we take the slope of position, we get the velocity function. But velocity also gives us direction. So when velocity is positive, v of t is greater than 0, the object is moving to the right or up. And if velocity is negative, less than 0, the object is moving to the left or down. So that's why we say speed is the absolute value of velocity, because even if we're moving left or down, we're still moving, and we just need to know how fast we're moving for speed, not necessarily which direction. Acceleration is the second derivative of position and the first derivative of velocity. So acceleration has to do with when we're moving, are we speeding up or are we slowing down or are we moving at a constant rate? So acceleration is the first derivative of velocity, the second derivative of position. So the functions go position, velocity, acceleration. So for example, half an hour from home, I was 25 miles away. So if t is in hours, then half an hour would be t equals 0.5. Remember, our position function is p of t. So our position at 0.5 hours would be 25 miles. That's how far we've traveled. If at that time I was going 65 miles per hour on 75 north, well, now this is my velocity, right? Because it's my rate of change. I have miles per hour. So the velocity at 0.5 hours equals 65 miles per hour, how fast I'm going. If at the same time I'm slowing down at a rate of 5 miles per hour, then my acceleration is changing. My acceleration at 0.5 hours would be negative 5 miles per hour squared. Right? Negative because I'm slowing down. Miles per hour squared because as we take a derivative or find the slope, the units of the input, the denominator, are always going to go up by 1. So we started with miles in our position function. V of t, velocity, is in miles per hour. That's our first rate of change. And then A of t is in miles per hour squared because it's the rate of change of the rate of change. Slope of velocity is acceleration. So the units for acceleration are miles per hour squared. So throughout the course, we will do lots of examples with motion, position, velocity, and acceleration. Let's talk about average velocity for a second. If f of t is the position function of a particle that is moving on a straight line, then in the time interval from t equals a to t equals a plus h, the change in position is f of a plus h minus f of a, right? That's the y minus y. And the average velocity of a particle is equal to displacement over time. So it's the change in position over the change in time. Right? Displacement is change in position over the change in time. So average velocity is actually the slope of position. Now this is important to note. Students always get this wrong. Average velocity is not the slope of velocity. Average velocity is the slope of position. If I were to find the slope of velocity, well, that would equal the average acceleration, because the slope of velocity is equal to the acceleration. If we're finding the rate of change of the rate of change, that's the next derivative. So average velocity is slope of position, which takes us back to our original slope formula. Change in y's over the change in x's.